All right, today we're going to crack open the engine of modern AI. We're going to demystify the one algorithm that lets machines learn, get better, and basically power our entire world. So yeah, let's dive right in.
So it really all boils down to this one super fundamental question. We throw the term machine learning around constantly, right? But what does it actually mean for a machine to learn? How does it go from being a blank slate to making these incredibly complex predictions?
And the answer, it's actually kind of simple, but it is so powerful. A machine learns by, well, it makes a guess. Then it figures out how wrong that guess was. And then it takes just a tiny calculated step in the direction of being a little less wrong. And it just does that again and again and again. We're talking thousands, sometimes millions of times. The whole game is about iterative improvement. So when you really get down to it, machine learning is basically a quest. It's a search to find the lowest point, the very bottom of the valley in this huge mathematical landscape.
Okay, so the fancy technical name for this whole journey is gradient descent. I know it sounds a little intimidating, but trust me, let's just break it down. Iterative? That just means you do it over and over. Minimizing a function? That's just a mathy way of saying find the lowest point. And the rest of it? It's literally just figuring out which way is downhill and taking a step. That's it.
Now, in a perfect world, the problem looks exactly like this. A nice, simple bowl. You start somewhere up on the rim, you look around for the steepest way down, and you just follow that path. That red arrow, that's showing you the path of steepest descent, and it leads you straight to the bottom, right to that point of minimum error. Seems easy, right? Well, spoiler alert, the real world is almost never this clean.
Okay, to really get a gut feeling for the math without getting bogged down, we're going to use what I think is a perfect analogy, the foggy mountain. So come on, let's go for a hike.
Picture this. You're standing on the side of a huge mountain. Suddenly, this super thick fog rolls in. Your goal is simple. Get to the absolute lowest point in the valley. But here's the catch. You can only see the ground right at your feet. That's it. You have no idea where the valley actually is. So, what do? Well, you probably feel the ground, right? Find the direction that slopes down the steepest, and then you take one step. Then you stop, feel the ground again, and take another step. And this right here, this is where our little story maps perfectly onto the algorithm. In this analogy, you're the algorithm. The path you're taking down the mountain, that's the sequence of tiny adjustments the algorithm makes. The steepness of the hill you're feeling out, that's what we call the gradient. And maybe most importantly, the size of the step you decide to take, that is a supercritical parameter called the learning rate.
And that learning rate, the size of your step, brings us to a really huge challenge. Because getting that step size right, it's a very delicate balancing act.
See, it's all about this trade-off. If you take these tiny little baby steps, you're gonna be super accurate. You're pretty much guaranteed not to miss the bottom of the valley. But, oh man, it could take you forever to actually get there. On the flip side, what if you take giant leaps? Well, you'll make progress way faster, for sure, but you run this huge risk of completely overshooting the valley and landing way up on the other side of the mountain, maybe even higher than where you started. Not good.
And here's the reality check. Remember that nice, simple bowl we saw at the beginning? Yeah. Well, real-world problems are nothing like that. They're much more like this incredibly complex landscape. There's not just one valley. There are ridges, flat spots called plateaus, and tons of different paths. Suddenly, our foggy mountain hike just got a whole lot more complicated.
And trying to navigate a terrain like this means you're going to face some serious challenges. Let's talk about the pitfalls on the path. Okay, so one of the biggest dangers is simply getting stuck. The source material uses this great image of a mountain lake. Think about it. You could hike down into a small dip and think, hey, I'm at the bottom. But it's just a little hole, a mountain lake. It's not the true bottom of the entire valley system. This is what's called a local minimum, and it's a huge problem because it can trick the algorithm into stopping, thinking it's found the best answer, when a much better solution is just over the next ridge.
Then there's another classic problem, the zigzag. You can kind of see it in this graphic here. Imagine the algorithm finds a really steep, narrow ravine. What can happen is it just starts bouncing from one wall to the other, zigzagging its way down. Sure, it's still making progress downhill, but it is wildly inefficient.
But of course, researchers have come up with some really clever ways to deal with these problems. There's something called momentum. The best way to think of this is like giving our mountain hiker a really heavy ball to roll downhill. It'll just power through the little bumps and smooth out those zigzags.
Then there's preconditioning, which is kind of like taking the map and squishing and stretching it to make the downhill path way more obvious. And then you have modern advanced optimizers, which are basically like giving our hiker a super smart GPS that adapts their step size and direction automatically based on the terrain.
Okay, so we've been on this whole mountain journey. Let's bring it all back home and talk about why any of this matters. Why is this seemingly simple idea the engine of modern AI?
Because this is the big aha moment. That lowest point we've been trying to find on the mountain, in the world of AI, that represents the point of lowest error. Every single time a machine learning model learns, all it's doing is using gradient descent to find the bottom of that valley, the one single spot where its predictions are the least wrong.
And once you get that, you see its impact is, well, it's everywhere. This is the main way we train pretty much all machine learning models. A slightly different version, called Stochastic Gradient Descent, is the absolute foundation for how we train those giant, deep neural networks. The ones that power image recognition, ChatGPT, all of it. It's even used in science and engineering to solve ridiculously complex systems of equations.
And you know what's really wild? This revolutionary idea. It isn't new at all. Not even close. The French mathematician Cauchy first came up with it way back in 1847. It was studied and tweaked over the next 100 years or so, but it was really the arrival of two things: massive amounts of data and incredibly powerful computers that finally unlocked its true potential. That's what turned this old mathematical idea into the engine of today's AI revolution.
So that leaves us with a pretty cool thought, right? All the incredible, mind-blowing complexity of modern AI, self-driving cars, medical diagnoses, all of it, it's all built on this one beautifully simple idea. Just take one small step at a time in the direction of being a little less wrong. And if all of that can come from what is basically a simple walk downhill, well, the really exciting question is, where will its next steps take us?